An empty beaker, 8.2 centimeters in diameter, is pushed 10.3 centimeters into mercury with that density, right? What is the net upward force on the bottom of the beaker? Assume the pressure above the mercury is 1 atmosphere. All right, 72.6 newtons. It's the net upward force on the bottom. Okay. So there's two ways to do this as I'm thinking about this, right? The first way to do it is to just use the buoyant force, right? So buoyant force is the density of the fluid times the volume of the fluid displaced times g, right? And this is our fluid that we're displacing, right? So this would be our density, right? That's going to go in there. The volume of the fluid displaced is going to be pi r squared h. And this is the volume of a right circular cylinder. You do need to memorize that because it's not in the data packet. So a sphere is in there, but a right circular cylinder is not. Okay, so the volume of the fluid displaced is pi times, and this is diameter and it's centimeters, so 0.0410 squared, right? And then the height is 0.103 meters. So let's figure that out. The volume is pi times 0.041 squared times 0.103. And that is 5.439 times 10 to the minus fourth. But that's cubic meters, right? It's actually, what, 0.5, half a liter, right, basically, which kind of makes sense. Okay, so now we're ready to go. So 13.6 times 10 to the third kilograms per cubic meter times 5.439 times 10 to the minus fourth cubic meters, right, times g, which is 9.81 newtons per kilogram. All right, so we are, notice the cubic meters cancel and kilograms cancel, and we end up with newtons. So let's figure this out. 13.6 E3 times the answer I just got times 9.81. And I get 72.57 newtons. Notice that we didn't use the 1 atmosphere above the mercury, right? We could, by the way, also do this another way. Do you want to know the other way? We don't even have to use this formula, although we're going to derive it anyway. Let me just show you the other way. Okay, so here's the other way, another way. We just want to find that net upward force, right? So here's the surface of the mercury. We stick this beaker down in there, right? Keep in mind that the forces that act this way from the mercury, they all cancel each other, right? This force cancels that one and all the imaginary horizontal forces. But this area here, right, that upward force is just going to be pressure times area, okay? And it's going to be a net upward force. That 1 atmosphere is pushing down on this, increasing the pressure in the fluid by 1 atmosphere, but it's also pressing down on the top of this as well, right? So the atmosphere really is neither here nor there. And that pressure is going to be rho GH, right? So we'll end up with rho GH as our pressure, and then the area is going to be, or H is this distance, right? Okay, and then the area is going to be pi r squared, right? Now, if you're paying attention, notice that this is rho g, and then h times the area. We're doing exactly the same thing we did in the previous way. So 13.6 E3 times 9.81 times 0.103 times pi times 0.041 squared. So it's another way to think about it, right? The net upward force is just the force is pressure times area. Pressure is this hydrostatic force, right? If I do all this, 13.6 E3 times 9.81 times 0.103 times pi times 0.041 squared, all of that is the same thing, right? It's 72.57. newtons. Which is, of course, this is where buoyant force comes from, right? So, yeah.